Okay, so what we're going to be going through today, you recall that last time we had gone over a process of selecting data sets from several sensors and from surveys, and we had some machinery to allow it to read those in and to aggregate them according to time slot. Do you remember that? Remember that? Okay. So this code basically goes and it reads in the survey data, the survey data here, and then the accelerometer, orientation, and gyroscope data, and it joins them together based on the time slot and the user ID associated with it, caches them. And then we defined a UDF, a user-defined function, which basically classifies whether or not a given survey was answered dichotomously, true or false. So 1 being true, if it is answered, 0 being false, it's not answered. We then defined some machinery to allow us to work with this data. So one of these things was a vector assembler. Does anyone remember what was the job of that vector assembler in life? What purpose? To what purpose was it created? For what purpose was it created? To what purpose was it placed? Does anyone remember?
So it's like a promise to arrange the vector in a certain way, so you can transform it according to that kind of pattern.
Good. And what pattern did it put in place? I'm gonna go back and scroll this so that its structure is perhaps more obvious, ladies and gentlemen. So here I'm going to put this in this sort of fashion, bearing in mind it's all one command. What is this doing? Sorry?
The assembler?
Yeah.
Put all data.
Okay, good. So it takes all of these items and it basically is going to put them into a column, a vector column called features, which is going to hold a vector. So each row, that column, the item for that column, is going to hold a vector consisting of all of these, the items gathered from all of these columns in whatever data frame to which it is applied. That English is not quite right, but in the data frame to which it is applied. So here we're applying this vector assembler to a data frame. And so by so applying, here we're just defining the vector assembler. Here we're applying it to a data frame. And so when we apply it, it's going to read data from each of these. It's going to create a vector consisting with each of these as its elements, and it's going to put it in a features column. So what comes out of this is going to be a version of this guy, but with one more column called what?
Features, and all of them, so that features thing has 6 elements in each row.
That's right.
Each vector within each row has 6 elements.
Exactly.
Like 6 doubles or something, whatever they are.
Yes, exactly. It's six doubles, I think. Okay. Next, we're going to extend it with a label column. And what's going on here? Why are we extending it with a column called label? Trying to rehearse these common steps. These are foundational steps for working with the ML library as a version 2 in Spark. So what's going on here?
So all the classifiers are supervised classifiers, so they need to have a label. So presumably.
Well spoken.
So presumably there's a standard input and standard for those. So yeah, and you have to have 2 things called, one called features, one called label.
Yeah, And so quite right. It needs one column to look for the features and one column to look for the labels. And those are indeed, if I'm not mistaken, those are indeed the default names. So it's going to look for a features column to find a vector of features, and it's going to look for a label column to dictate the ground truth used in the supervised learning. Later, I actually go, and probably if you want to live on the edge, you could probably get rid of these things. But I actually go and formally specify that those are the column of features and these are the columns of labels, okay? So in the ML library, and it's not just this, but this is one exemplar of it, we will often have situations where the mechanisms, in order to be arranged to work properly, they will have some notion. There'll be mechanisms, and the mechanisms will have a notion of where do I get my input data, like from which columns, and where do I put my output data. And we string those mechanisms together, one after the other, in a pipeline. And that allows it sort of one to read from the last, for example. And so this is indicative of that. So we're creating features column and a label column so those can be consumed by this decision tree classifier when it is fit to a given data frame later. Okay?
But the features column is not an output column. It's another input column, isn't it?
It's another input column, yeah. It's a label column.
Yeah.
What's called a labeled column. So here we're telling the decision tree classifier, well, okay, we have to be careful with that. Here, the features column, the label column, from the standpoint of the decision tree classifier, are those input columns or output columns? Those are input columns. The decision tree classifier, to do its job, needs to know where to find the ground truth information and where to find the vector of features, right? In order to know how's it doing in its classification, to do cross-validation, or to do supervised learning, it actually is going to use these information about the label, right? So from the standpoint of the classifier, when it's being applied to a data frame, it's actually, both of these are input columns for the classifier. It's going to take data from this data frame for each of these columns. Do people understand that? However, from the standpoint of this assembler, this is an output column. Why do I say that?
Because it's creating it.
Because when we transform this data, it's creating the features column. So ladies and gentlemen, in Spark ML, there's this distinction between, on the one hand, transformers, and assembler is an example of a transformer, and estimators. Here we have an example of a transformer, okay? So it's transforming this. Here we're estimating a model based on this. Later, we're taking that model and we are using it to transform. So the model that we generate by fitting it on this data, that is used to then transform a data frame. What happens if we transform this data frame with the model? What's going to happen? So this assembler was a transformer. We applied it to a data frame, and it yielded a what? When we apply this assembler to a data frame, what does it yield back?
A data frame.
Indeed. When we apply a model to a data frame, what does it yield back?
Does it add a column, which is the predicted? Okay, so is your code down to this point now? Oh, I haven't run that code.
Oh, okay.
I ran it up to,
So actually
okay, now
I
create a decision tree classifier.
I think.
Yeah.
Could you please see this? Do you have defined this fraction of training? Probably this is one.
Oh,
this is
it should
one.
be fraction subset. Sorry.
Subset one, yeah?
Sorry, subset one. Oh gosh, Gosh, I thought I fixed that last night, but I was not operating it with all cylinders last night. Okay, yeah, so that's fraction. Thank you so much for capturing that. Yeah. Okay, ladies and gentlemen. Okay. So yeah, I'd like it to get down to this fit, although it might actually be fine that it just operates up here. When you applied the vector assembler, it probably needed to get all the data from the database too.
I ran that.
Did it take a while?
No.
So maybe it's just a promise. Yeah. So ladies and gentlemen, here are these transformers. This is processing this data frame and it's yielding a data frame. And in order to process the data frame, it's taking this in, it's getting its information as a model from certain columns, and it is using it to predict output information. Okay. So here we are creating this model fitting to this data, and then we're applying it to this data, to the same data. I'd like to avoid that, and it's that, with that in mind, that I have this component here, this fraction subset 1. So what I'm doing here goes beyond what we saw last time, but it's the natural extension of it. So I am basically dividing up the data here into different fractions, to different subsets. So I'm going to go execute this so you could see it. You gotta love Spark. You gotta love Scala. Look at that. Isn't that elegant? Look at that. What does that do? What does this do?
Yeah. Just randomly.
Yeah, it randomly splits it into, with this fraction in the first one, this fraction in the second one. It randomly splits DF labeled.
So random split means that essentially each row has a 50% chance of going into one.
Well, in this case it is 50%, but in general it might be 10%. I think actually it may be more than that. I think it actually, this first one has what we, let's check, DF labeled subset 1 dot count. I think it'll be exactly that fraction of the total,
Right.
well within integer rounding, right?
Now it actually has to go through and hit the database.
Indeed. This is just a promise.
Yeah. But the whole thing so far has been just a promise.
It's just a promise. Yeah. When does it need to go beyond a promise?
I mean, it needs the data. So when you're outputting or something.
Yeah, when you're outputting, for example, it'll need to go
What is a
beyond
side
it.
effect?
You could have a promise for a side effect, but certainly when you're outputting, when you're writing to a file, etc. Yeah.
But if you don't have a side effect, it's just an equation that sits there in space and does nothing.
If you're not consuming it in some way that requires looking at it or what have you, there's other cases too. I think which also have some relevance, but certainly a key one is you want to look at the data. You actually want to look at it. Okay, so ladies and gentlemen, what is this weird thing that array is on the left? I'm saying it's weird because to someone who's unschooled in Scala, it may be unfamiliar. What's going on here?
It's using pattern matching.
Pattern matching. Unapply, ladies and gentlemen. So it's calling unapply on array to take apart the array that's returned by this and label the first part, the first element of the array, DF labeled subset 1, the second one, DF labeled subset 2. So this is a val. It's declaring these variables to refer to the two different components of the array referred to here. And in general, this is an unapply operation. This is an extraction operation using just like pattern matching, right? It's taking apart the pieces and giving them each names. Okay, Okay, so we're doing that. So then we can do things like train it on one part of the data and test it on the other part. Right? Right now, here we are fitting. We're estimating a model based on the entire data, and then we are applying that model to that same data to get back a predicted data set, and we're evaluating that data set. But that's not really fair in the sense that we're assuming we have, privileged knowledge to the true value. We're training it on that, and then we're just applying it to itself. It's not really a fair comparison. It can lead to overfitting, among other things. So what we're going to do is we're going to evaluate this. We're going to train it on a subset, and then we're going to transform
The other one.
the other one. I'm going to test it on a different subset and evaluate that. What do you think?
And then you do this 10 times for
You could do it 10 times.
whatever.
Yeah. We could do it 10 times, but as we'll soon see, it can do it for us 10 times.
Right.
Yeah. Okay, so here it's still doing its work. Are you folks hitting the database at the same time?
Yeah.
Yeah. So probably that's factoring a little bit into the slow speed.
I just had to wait until you were done.
Okay, good call. Yeah, I was hoping people could do it during the soliloquy that preceded it, but okay, so that's good. So let's let it do that. Let's let it do its thing. But meanwhile, let's go look at the home exercise, shall we not? What do you think? Okay. So the home exercise that I asked you to undertake, so I'm going to stop this here